This is Dr. G.S. Garewal, the Faculty of Electrical Engineering. I'll be discussing the Tauberian theorem, which is applied on the electrical circuits. The name Tauberian theorem, this theorem has been devised by Leon Charles Tauberian in the year 1883. The technique proposed here is used to simplify the electrical circuits. What we do here in the Tauberian theorem is that if there is a linear two-port network comprising of the voltage sources, current sources and the combination of resistors, that can be replaced by an equivalent source, and that voltage source will be having a resistor in series connected to that. So, this theorem is used to simplify electrical circuits involving AC or DC. There are the steps which are required to solve the Tauberian theorem. The step number 1, when we look at the circuit, we need to see that there must be voltage source, current source or a combination of resistors that must be present in the circuit. Point number 2 is, first of all, we need to turn off the independent voltage or current sources if any. That is, if there is a current source, we need to replace it by a short circuit, and if there is a voltage source, we do it by the short circuit, and current sources are replaced by open circuit. When we have this, then the next step is we need to look into if there are dependent current sources in the picture. If there is a dependent current source, then we do not do anything to them, because the value of them will be controlled by the elements which are present in the circuit. And the other thing is, after that we need to look into on the application of the theorem, that where these Tauberian theorems can be applied. So, that we will discuss later on. Then the other point to be followed is the evaluation of the Tauberian resistance. What we do in a circuit, we see that there is a load resistor which is present. Our first step is to remove the load resistor from the terminals. At those terminals, the open circuit voltage will appear. This voltage is known as Tauberian voltage. When we look at it, then we try to find out the various means to find out the Tauberian voltage. Either we apply the Kirchhoff's voltage law to find it out, or if we see the complications in the circuit, we then go for nodal voltage analysis to simplify that. Our objective is to find out the open circuit voltage called Tauberian voltage. Then we see that we are provided with the after removing the sources, we see in the circuit there are the combination of resistors which may come in series or in parallel. So, from the point from where we have removed the load resistor, looking into from these points, we start combining the resistances. Then whatever the equivalent resistance we find out, that is called the Tauberian resistance. After evaluating these two quantities, then we say that whatever be the entire linear network which was comprising the voltage source, current source and the series combinations of resistors, that is now replaced by an equivalent circuit, and this equivalent circuit is having a voltage source which is having the VOC, that is the Tauberian voltage, and it is having a small resistor R Tauberian in picture. This R Tauberian is nothing but the equivalent resistance which we have solved while analyzing the circuit. The next step is we reconnect back the load resistor into the terminals from where we have removed it. Now, we see that we have a VOC called V Tauberian, and we have a series resistor with that called R Tauberian, which is our R equivalent, and we connected load resistor back into the picture. Now, when we do that, at that point what we have observed that the current through the load resistor will be the voltage divided by the resistor in the circuit, that is VOC or V Tauberian divided by R Tauberian plus load resistor value RL. So, practically there will be a circuit that circuit will be, suppose we consider a circuit where on the left hand side we draw open the voltage source with a value of 32 volt, and then we have a combination of resistors like a 5 and 12, then later on 1 ohm, we can put them in series or parallel, and we can put a current source in the picture, and we can have a load resistor RL of 6 ohm. If we make a circuit, the points to be noted is that first remove the independent sources if any, remove the voltage source with the short circuit, current source by open circuit. Later on, step number 2 is that we need to find out the open circuit voltage, and the step number 3 is we need to find the equivalent resistance or the R Thevenin and making the combination of resistances. And point number 4, we look into the V Thevenin magnitude, which can be obtained by either applying the Kirchhoff voltage law or the nodal analysis which seems fit to it. Once we have these, then we replace the entire network by a voltage source in series with a small resistor. This combination is called Thevenin equivalent of the entire network. Then the last step is we reconnect back the load resistor, then we find out the current flowing through the load resistor. So, Thevenin theorem is very much important for solving the electrical circuits as well as the power system analysis, because when we look at that, we find out that in the DC circuits straight away we apply this theorem with very ease. When we talk about AC circuits, when we are having a supply of like with the frequency of 50 hertz, there is no complication in working with the circuit. But later on, if we talk of high frequency circuits where the frequencies can be megahertz or kilohertz, then this circuit cannot be simplified as per the Thevenin theorem. The complex techniques will be required to synthesize to simplify such circuits. When we are doing the steady state analysis, we can use the Thevenin theorem, but it has a limitation when it will be applied for the transient analysis, because the transient analysis the signal response varies from 2 milliseconds to 5 milliseconds, and there is no information which will be provided to simplify the Thevenin theorem when we talk of high frequency circuits. We talk that whether we have the voltage source or the current source or the resistors, it means we are talking about the two terminal devices. So, the Thevenin theorem is applicable only to the two port terminal devices, not, and whenever we talk of high frequency currents, this Thevenin theorem is not applied. Also, when we talk on of power system, all the transmission lines, they are having the lumped parameters, and the whatever resistances combinations we are getting from the power system, we synthesize so that we can be able to find out the equivalent value by simplifying it later on. But when we talk of power dissipation, suppose there in a 3-phase AC network, there are a lot of devices, and when we are talking of the high power values where the values voltage values are in kV or currents are like 200 ampere 400 ampere, then the power dissipation over the lines will be quite high. So, if we say that if we constitute a 3-phase AC network and we try to do the Thevenin theorem analysis on it, and we find that there will be the power dissipation across various devices. That power dissipation will be different across the different devices depending upon the current carrying capability of such devices. If that be the case, then when we replace the Thevenin circuit by its equivalent circuit, then that power dissipation by a Thevenin equivalent will never be equal to the power dissipation by the various devices connected in the network. So, this concept of power dissipation is not applicable, we call it as a limitation for the Thevenin theorem, and the Thevenin theorem is applicable when the elements in the circuit are all linear in nature. Linear means that the device, all the elements of the circuit, they must be obeying the law of linearity property, that is additive property as well as homogeneous property. So, if they are doing that, then only this theorem will be applicable, else it is not. If suppose there in the if we have a circuit, in the circuit we add a diode, or in the circuit we add a thermistor, or we add a transistor, in such cases addition of one nonlinear device makes the entire circuit nonlinear, and this Thevenin theorem is not applicable to such circuits.